votes. Adam, you didn't vote, but it's like natural selection in a good sense. Okay, and so we do it in 9 days, right? Not coming Friday, by next Friday. Okay, so here the next month, typically after presentations, we shouldn't have anything due, but since it is end of semester, it will be a little more active. So a Monday after you do presentations, there will be homework which will be based on your presentations. Basically, you listen to each other and make notes and then submit it as a homework. Just answering some questions, given equations, and whatever is provided. And if you do not know how to answer some of the questions, then presenter of this subject is responsible. Okay. So there is no October 39 for sure. I think there is a October 30th. So if you are not super busy, which I cannot imagine, but if you have a little time to invest and want to get best benefit for the class from practicing homework, it would be beneficial if you try to do it by Friday. But I understand it is only as for like 200% credit. But if you submit it by in a week, by next Wednesday, it is fine. So just a chance. Okay, and this extra credit problem, I need to think, because I'm planning to solve it, maybe at least partial in public on Friday, at least half of it. So if I show it, then it will be kind of not quite reasonable to credit anyone who solves it later. Therefore, the schedule. But this equation is what we are going to get at the end of today's meeting. And the normalization factor is something that one can get by taking square of this function and integrating. And the factor that will pop up here is an important thing for our later progress in class. And we were discussing before, normalization is needed for any observables, and for harmonic oscillator, there is an additional value of correct normalization. Okay, so we are making connections between time-independent Schrödinger equation and ladder operators right now, and there will be no new ideas, almost no new ideas. It is even with all shortcuts, it is quite math-intense subject. So briefly, what we did in the last few meetings, we are considering, yeah, there is nothing interesting on the board. I'll better focus on the class. So we are looking primarily on molecular vibrations, but there are some other examples when things are oscillating harmonically, and we assume that these vibrations do have quantum features. So the particle that is oscillating is quite small, rigidity constant, elasticity constant is quite high, so the frequency is in the domain of infrared signal. And if you look on the position of oscillating entities, they are distributed. There is some uncertainty and distribution of probability to be here and there. So we plug information about this quadratic potential into Schrödinger equation, try to solve, and in order to avoid recursive solution for expansion coefficients, we are using ladder operators, where Strawman tries to jump below, acting annihilation operator to the ground state gives 0, and from this equation we got ground state, which is Gaussian distribution. And then we are subsequently applying raising operator to get first, second, and possibly next states. We are going solve by hand ground state, number 0, first state, number 1, and second state, number 2. And then we will see a trend or just borrow it from books, because all exercises should have some limit. And another thing we did, we expressed those Strawman operators, raising and lowering operators, or some people call creation and annihilation operators, as a linear combination of position and momentum, like position minus imaginary unit times momentum, and there are some factors to make this operator dimensionless. And by this operation, we can reformulate total energy operator, Hamiltonian, as product of creation and annihilation operator and nothing else, which is, it has a lot of abstract math in this procedure, but then like Hamiltonian H equals A plus A. It's quite short. Maybe this is one of the benefits of doing this operation. So yes, I think it is what we went through, right? Position and momentum with some coefficients, ground state. And here is the thing that stays my goal for today. Here is the thing that would benefit from extra credit problem from the currently assigned homework. And here is the thing that make life beautiful from the point of view of a mathematician. We are not mathematicians. Maybe it's all ugly and not attractive, but it's better than it could be. So here is the property that I will focus on, and we slowly will derive. So by applying raising creation operator to ground state, we are going to get state number 1, right? By applying raising creation operator to state number 1, we are going to get state number 2, right? By applying raising to state number 2, we are going to get state number 3. But if we carefully perform normalization for each of them, we will identify a very interesting property. If the functions here are normalized, then action of this creation operator will not only create next more senior state, but it will also accumulate a factor that will be literally equal to square root of the number of the state. And this this is basic conclusion from what we are going to get today. If you agree with this, the rest are just mathematical details, which are quite heavy and maybe unpleasant, but this form is rather symmetric. So, and if we need to continue this procedure infinitely, then applying creation operator to eigenstate of harmonic operator number n, we will get eigenstate of harmonic operator number n plus 1 multiplied by square root of n plus 1. So maybe when you were taking calculus, some of the lectures were organized as first offering theorem and then spending an hour to prove it, right? So in some sense, we are on a similar note, but proof is a little less important and valuable than in math. Most important is this idea, and these properties, this property that we are getting right now, will help to fulfill a dream. Well, it's a very humble dream. It's not like a dream to make everyone happy, healthy, and rich. It's like a tiny dream how to make consideration of quantum harmonic oscillation simpler. But the dream is to avoid any differential operators, avoid wave functions as continuous distributed functions. Speak only in space of expansion coefficients. Speak about each quantum state just as a vector of expansion coefficients, speak about any operator as a matrix. So if this is possible, then it's still many symbols when we process them, but the logic is very straightforward. And there are much less unexpected challenges, because when we deal with differential equations, calculus, derivations, there are so many chances to make an error and get to a wrong answer. When we are processing matrices and vectors, it's quite straightforward and is easier to do. I heard some voice. Is it something wrong with me, or online attendees were asking questions? Okay, maybe something is wrong with me. Okay, microphone is unmuted for Joshua and Nate. So this is the last slide which I really want to arrive to. And if you will be short in time, I'll just skip some derivations. So the application of creation operator to eigenstate number one will let me speak more, and maybe it's more important to speak about this slide rather than derivation, because there will be absolutely no new ideas. Everything will be only support for it. So the solution of time-independent Schrödinger equation for harmonic oscillator has there are several solutions. These solutions are represented, have the same functional form. They are represented as decaying Gaussian exponential times polynomial of independent variable. And for ground state, this polynomial is represented by zeroth order, just by one. And as we escalate up to higher energy, higher number of excited state, we have more senior polynomial, like zeroth power, first power, second power, third power. So we continuously escalate the order of this polynomial. And before we learned ground state, where polynomial is just equal constant one. First order, when polynomial is just equals x, first order. And today we are getting second order, where the most senior power is 2. And main problem in finding these solutions is to find expansion coefficients in front of polynomials of this function. So here in front of x squared, we will have 2 alpha, which is combination of these constants like mass and frequency. Then there is 0 in front of x and is constant 1 in front of 0. And the main dramatic question is how these coefficients will change as we go up. Okay, so one thing. And regular textbooks in physical chemistry which focus on minimal amount of information, they stop studying harmonic oscillator by finding these functions and these expansion coefficients, then drawing probability distribution, and then tell enough, let's go to the next subject. I really want we do a little bit more than that. So we will overview, and I have no doubt that you could do this operation yourself, just apply an operator and get this function, and then get this normalization. But if we carefully do normalization to this function, then we will get factor 1 over square root of 2. And if you carefully apply without normalization, we take normalized phi1, perform this operation, then we get thing without this 1 over square root of 2. And if we continue to escalate it further and further to more senior members in the row, this factor will be smaller and smaller, 1 over square root of 3, 1 over square root of 4, and further. And by comparing these two expressions, and then multiplying both sides by square root of 2, we are getting this relation. And then we are not going to make rigorous proof of other terms. We assume that this trend will continue for each term, so that who can find an error? Oh yeah, thank you, Sybil. N plus 1. Sybil plus 1. Okay. So actually we are starting looking for support information to get to this idea, and here is the plan. So we apply creation operator. It will include the derivative. Then we can just plot the result of outcome, and then we will set up problem of normalizing the second state. This is quite painful procedure. I have no chance to complete it in 20 minutes, therefore, but I'll at least show the path. So it is in some sense straightforward, but it will take at least like 30 minutes to derive it carefully. And after getting result of integration, which will be split on 3 independent terms, we will get actual thing that we are looking for. So a factor accumulated by promoting junior state to senior state. Whew. Okay, at least it is clear for myself. I don't know if makes sense, more or less. Okay, yeah, thank you for the support. So first state includes x and this exponential factor. The raising operator includes position and momentum, and one can put minimal amount of factors in front of momentum, and then it will be, they will just arrange it this way. So we are replacing momentum with the derivative of a space. I think the factor alpha, if I missed to introduce it, is this combination. So mass, frequency, and Planck constant. So it's there is no much of physical or chemical meaning. It's just combining 4 symbols into one to have a shorthand notation. And the operation that we are going to do is in the last line. So from position, we have this alpha times x. From momentum, we'll have derivative. And we do not have imaginary part because it was imaginary one from definition and another imaginary unit from one from definition of creation operator, another from definition of momentum. So x and ddx. And then these two things are applied to product of linear function and exponential. So the plan is that it will be at least 3 terms. So first term, if you just multiply this factor by these 2 functions, and then we will have derivative of product. So derivative of first times second plus first times derivative of second. There are no new ideas in the slide. It is the same thing that we saw before. It's just typed in a better font. So when we practice the 3 terms, then multiplying the factor onto this linear and Gaussian exponential, you will get the linear becomes squared, right? Because 1x comes from the definition of creation operator, and another x comes from the first state. So we get square, and we keep this Gaussian profile. Then if we take derivative over x and keep exponential function, it will have this factor. And if we keep linear and take derivative of exponential, the derivative of e to the minus x squared keeps exponential and put derivative of x squared in front, which will be another x. And then we'll have one x from creation operator and another x from the derivative sorry, right answer from the wrong reason. One x was just a part of the first state, and second x comes from derivative of exponential. And then we identify that the third term and first term are absolutely identical, and we just combine them into one and put factor 2 in front. Make sense? Is it better that we look pre-made slides, or you would enjoy if I derive or call someone to help me? What is your opinion? Equally? Okay. Okay. Yeah. No. Today we'll go through slides, but maybe in the future I'll try to add some derivations, because otherwise it's. I imagine myself in the classroom, I would already fall asleep just trying to follow the slides. Okay. So 3 terms. First and last are identical, and they're combined. And then in these terms, we can put we identify the same factor. The Gaussian exponential is the same for all of them, right? And then after putting it out of brackets, we will have 2 alpha x squared as a first term and minus 1 as a second. So we have got the result of applying creation operator to the first state, but it is not normalized. We do not know what will be the normalization factor until we practically do it. So we do need to normalize the second state. And here were the what we will do in a couple of minutes. So I didn't brought any figures of seals or camels, because 3 humps will be too exotic. So if you have some ideas what which figures to use for next year, please share. Which natural object has this shape. But if you want to plot this function, we can, in some sense, we can project and extrapolate our experience from the particle in the box. So the ground state has one maximum. Second state, it goes 1, crosses 0 and down, and then approaches 0, right? And the third state goes up, crosses 0, down, crosses 0. So it's 2 maximum and 1 minimum. And if you take absolute value square, it will be 3 maximum. So we expect the same shape, same qualitatively the same shape here. Basically, the number of nodal points, number of times the wave function crosses the x-axis, qualitatively determines what is the value of kinetic energy, what is the value of momentum. More frequently it crosses 0, it means it more dense fringes, it means it corresponds to more vivid kinetic motion. So ground state doesn't cross x-axis, and highly excited state, they will cross it many times. And the only thing is how to project this knowledge onto this second state and what to do with edges. So if one wants to plot it, then one can first plot the quadratic function with this constant defines how sharp or shallow it. Then by putting -1, one shifts the origin so that it will cross the y-axis at point -1, right? And then we multiply this parabola, which intersects x-axis in two symmetric points, by the Gaussian profile, which is always positive but decreases to 0 heavily. So in the middle, and if you do not have computers and you want to plot product of functions, we just multiply signs. So minus times plus will be minus, and it will be something non-zero, substantial. So minus. Then we project the points where at least one of the functions crosses 0. So two 0 points. And then to the aside from this point, we have positive times positive. Positive function, positive, positive plus. And then the exponential is much more aggressively approaching 0 than quadratic function goes to infinity. And by the multiplication, we get zeros. So, but since this fight and struggle between parabola and exponential goes for a little longer time, and parabola is more vivid than linear function, these tails expand to a little longer distance. And if you compare to ground state and first excited state, these non-zero regions expand to a little bigger area from the center. Make sense? Okay. Thank you. And then we can take absolute value squared and get this features. So if one offset this absolute value squared by the value of eigenenergy, then and put it together with the potential energy, then one can arrive at such figure. If you are looking for teaching career, at least what I've heard, this is another minimalistic point in this class, which needs to be delivered even if we have less ambitious course. So first thing is figure like this for particle in the box. Second minimalistic point is the figure like this for harmonic oscillator, and those are famous and delivered in all courses, because even with this complicated mathematical complications, those are problems that can be solved literally, exactly, and they're worth of studying as a fundamental for other things. So if someone tells me show two figures to summarize this class, I probably would do this for oscillator and for particle in the box. There is another thing that is not a big secret, but I didn't focus on it, and we will revisit it with more details. But the energies of this eigenstates, they all are proportional to frequency of oscillations. And in order to let me tell something that you may like, and it may give connection to real world. Let's for a minute forget about everything about quantum and just assume that we have a polar diatomic, like sodium chloride. They have a different charge, or maybe it's hydrochloric, better. So it stands alone as a gas, hydrochloric acid, HCl. So the charge on H and chlorine is different. And if we apply electric field, it will orient it along field. And if you change field, it will contract and expand this bond. So the bond length can oscillate, and it has its specific frequency, right? So if you will change electric field so quick or so slow, so that the frequency of changes of electric field will match the frequency of these oscillations, it will pump energy onto oscillations, and they will increase amplitude, right? So like resonance condition. And this frequency is specific for each pair of atoms, or for each group of atoms. And what we discussed right now is a principle of infrared spectroscopy, right? By agitating it at certain frequency, we can make certain groups of atoms to oscillate. And main feature is resonance condition. So the frequency of light must be equal to frequency of oscillations. Okay, now let's see connection between these words and what we see on the board. If we, in quantum theory, which is part of physical chemistry, excitation can be considered as just sending a photon of a certain energy. So if you send a photon of energy which is equal to difference between these two levels, then we expect to promote system from ground to excited, right? And now let's see what is the energy offset between these levels. So h omega 3/2 minus h omega 1/2. So it will be h bar omega, right? So the energy of the transition must be equal to frequency with which this molecule is oscillating. So it's same resonance condition. If we want to promote molecule from ground to excited state, we should perform the same agitation of the right frequency. Just we will, instead of continuous oscillations, we will assume that it is quanta of given energy, of given frequency. But this energy difference would correspond to infrared spectroscopy. And if we continue to send photons of the same energy, look, here the offset is 5/2 minus 3/2, we will again 1 h bar omega. So with the first quantum, we promoted from ground to first. With the second quantum, we promote to the second. And then if you have high intensity radiation of a resonance frequency, we'll just escalate and go ladder by ladder to higher and higher state, which will correspond to the amplitude of oscillations increasing, oscillating it more and more vividly. So maybe it's not very rigorous, but it's some qualitative connections to real life. Make sense? Okay. Okay. And now the part that is pleasant to overcome, but not pleasant to do. Therefore, it is your extra credit thing. So here is the second state wave function, or normalization factor, and 2 is unknown. We do want to take it absolute value squared and make sure that it equals 1, and then solve for n2, right? And best idea is just to fall asleep and then wake up when you see the answer, because the same. Are you watching the TV series Foundation? Or do you like science fiction? It's good. And as in many science fiction episodes, when people travel to distant stars, they are hibernated and they wake up and they are at the different planets. So it would be best to do the same here. Just hibernate and then wake up then when answer is ready. So this 2 is a plus b or minus b, and when we take square of the wave function, there will be 3 terms, right? So second power of the first term, which will be 4 alpha square x4, then -2, and this time without change of the power, 2 times 2 alpha x squared, and then from the last one will be 1, and then the power of this exponential thing is multiplied by 2. So it's instead of alpha x squared divided by 2, just alpha x squared. So there are 3 integrals of a polynomial multiplied by Gaussian exponential of 0th order, and this one is the simplest. If we need to, if we would solve it not as a personal assignment of the whole problem to everyone, but as a group, we probably should split responsibilities, and one does one integral, another second one, another third one. I would select this one because it's the simplest, right? So integral of Gaussian function will be square root of pi. Adam, yes? Okay. Then when we have independent variable squared by Gaussian function, it's a little more tricky, and when it is fourth power, it's even trickier. So basically, we need to find these 3 integrals, and we can call them just to have some notation, not to get lost, like based on the power. So I0 for power 0, I2 for power 2, I4 for power 4. And to make this procedure simpler, we can select new variables where the square root of alpha times x will be new variable. Since we're integrating from minus to plus infinity, the limits of integration do not change. And one variable, one symbol is always better than 3. Then we can, this expression will look simpler. So if you do the substitution, then infinitesimal derivative is changing, and the 0th order integral will be square root of pi times this unknown n2 squared, and 1 over square root of alpha will just come from change of variables. For the second, we likely need to practice integration by parts, right? And the Gaussian function cannot be submitted under the differentiation sign, so we need to practice the derivative of polynomial function, put it under the derivative sign. Oh, okay. I think I skipped the most interesting part because I was assuming that we will finish soon. But if one carefully does it, one will see that things will cancel. It will be proportional to normalization of the state number 1, and they will be different by a factor of square root of 2. Whew. I promise I did it in my time, but it was no fun. Okay, so if it is done correctly, then upon normalization there is this factor, and here is normalization of first, here is normalization of second, and we get this difference, and extract the, thank you, Sibel, for finding this, this general relation, how the creation operator convert junior eigenstate into senior eigenstate. 49 minutes. So thank you for your patience. Have a nice meet of the day, and looking forward to see you in the lab. We will continue through the skills we need for the projects and for your presentations. So meeting is done. If everyone is welcome to disconnect and depart. If there are some questions, I'll stay and answer.